So hello guys. So today we'll be talking about machine learning interview questions and answers part 2. So today I'll be discussing about what is feature in scaling and why and where we need it in machine learning, and what is normalization and what is standardization. The next question is like what is the bias variance trade-off, and then define the overfitting problem and why it occurs. And of course, what are the different methods ways to avoid overfitting in ML. Okay. So before proceeding, let's quickly recap what I have already discussed in last video. So in part one, I have discussed like what is ROC AUC curve and how to interpret it. So like we discussed to decide the threshold for the classification, we use ROC and AUC curve. And of course, then we discussed what are the type 1 and type 2 error, how you explain about recall and precision, and what is F1 score, and of course what is the difference between R square and adjusted R square. So if you want to know the explanation about these questions, then of course please refer my previous video, and let's start with today's agenda. Okay, so what is feature scaling basically? So in general, if you talk about our data set, so in our data set, we have different variables, and the different variables might have different range values, right? For example, if we talk about the units, right? So if some units are in kilos and some units are in grams, so kilos will be 1 kilo, 2 kilo, 3 kilo, right? And in grams, values might be 1,000 grams, 2,000 grams, etc. So that's where, if we talk about the feature wise, then their range differs, correct? So hold on, we'll take an example and we'll understand it clearly. So and then if feature ranges, I mean features have different range of values, then the feature with large range of value will start dominating against other variable which has less range, basically shorter range. Okay. So models could be biased towards those high ranged features. So that's where if we have different range values, and a feature with high range could start dominating against the feature with low range. So that's where a model will be biased, and we don't want this behavior in model, right? So that's where to overcome this problem, we do feature scaling. So that's where if you face this kind of problem in your data set, then you have to opt for feature scaling techniques. The goal of applying feature scaling is to make sure features are on almost the same scale so that each feature is equally important and make it easier to process by most ML algorithms. Okay. So now let's understand, we have a data set, like we have a column country and age and salary and purchased. Okay. So this is like, for example, bank is giving some offer like in some of his services, for example, term deposit service subscription. So based on salary, age and country data, whether he will subscribe for a term deposit or not, some data set. Okay. So anyway, we are not going to focus on this purchased, just talk about like age column and salary column. Okay. So here you see age has value like 44, 27, 30, like 2 digit numbers, and salary have a 5 digit number like 73,000, 47,000, 53,000, likewise. Okay. So salary feature has higher values and age feature has lower values. So that's where if you start training a model on this kind of data set, then of course salary feature will start dominating. But we don't want that kind of behavior. So that's where we go for feature scaling. Okay. So here, if you see age column has range between 27 to 48. So 48 is the maximum value and 27 is the minimum value. And salary column has range between 47,000 to 78,000. So maximum value is 78,000 and minimum value is 47,000. Okay. So feature, so let's call age as feature x1, and we have a min max value like this. And then x2, that is a salary column that has min max value like 47,000 and 78,000. Okay. So what problem it may occur. So see, so there are certain algorithms which are distance based, like k means, k nearest neighbor algorithm. So that's where we calculate the distance between different features, right? So if you see this particular diagram, and if you are calculating the Euclidean distance, so what we will do, like in x-axis we plot x1 and x2, that x feature, and in y-axis we can plot y1, y2, that is y feature, that is salary. X-axis will denote the age feature and y-axis will denote the salary feature. Okay, there are two axes. And then here the point like how we draw like x1 y1 and x2 y2. So here x1 y1 will have like x1 is 27 and y1 is 47,000, and here x2 will be 48 and y2 will be 78,000. And if you project those in x-axis and y-axis, then you see here like so your x has like higher range, right, and y has lower range. So that's where, so this x feature like so the feature which has a higher range, right, they will start dominating. So that's where the algorithm which are based on like distance measures, so those create a problem. They will start biased, they will be biased basically. So that's where we go for feature scaling. And what are the different methods for feature scaling, like normalization and standardization. So these are the two mainly used techniques in machine learning domain for feature scaling. Okay, so let's understand what is normalization and what is standardization. Okay, so before moving that, let's understand like ML algorithm which need feature scaling. So I have some examples like the which are the ML algorithm which are more, I mean, affected by feature. I mean high and low range features basically. So, like K means, so it uses the distance measure. Then, of course, if it uses distance measure, then it will be affected by different range of features. So that's where for K means we go for feature scaling. Similarly, for K nearest neighbor, so it also measures the distance between pairs of samples, and these distances are influenced by the measurement units, right? So for K nearest neighbor, also we go for feature scaling, and then principal component analysis, that is PCA, one of the mostly used dimensionality reduction technique. So this also get the features with maximum variance, right? So this also feature dependent. So that's where we go for feature scaling. Then of course we have artificial neural network and gradient descent. So they are based on gradient descent technique. So like in gradient descent problem, theta calculation becomes faster after feature scaling, and the learning rate in the update equation of stochastic gradient descent is the same for every parameter. Okay. So if you don't know what is stochastic gradient descent, then I mean you can this particular point you can leave for now. I will explain in next session. So, but for timing, you just understand for gradient descent is we need feature scaling. Like if you have different range of features, okay. So one more important point, like if an algorithm is not distance based, then feature scaling is unimportant. So there are certain algorithms which are not dependent on distance measure basically. So that's where we don't need to go for feature scaling. So like some example like nerve-based algorithm, linear discriminant analysis, and tree-based models, right, including gradient boosting and random forest, they don't require feature scaling basically. And the algorithm like KNN, K nearest, PCA, these are distance based. So that's where we go for feature scaling. Okay. So now let's understand what is normalization and what is standardization. So these are the two techniques used for feature scaling. So what is normalization? So normalization is also known as min-max normalization or min-max scaling. Normalization scales the values in the range of 0 to 1. So if you apply normalization technique in a particular feature, then after applying normalization, you will get all the values in between 0 to 1. And what is the formula? Like if you want to normalize, so just do x minus mean divided by max minus mean. So like let's understand with an example. So we have age column and we want to normalize the age value. So what we will do? So first we will identify what is the mean value for age column. So in age column, mean value is, what is the mean value? It's 27, right? And what is max value? Max value is I guess 48, right? Then a normalized value will be x norm really for 44 minus 27 divided by 48 minus 27, and this will give you this value, okay, against 44. So of the normalized value of 44 will be this. Similarly, you can calculate for 27. So it will be 27 minus 27, it will return to 0. Okay, and in case of 48, that is the max value, like 48 minus 27 divided by 48 minus 27, it will come as 1. Okay, so these are the normalized value basically. and this is how you can calculate it. And similarly for salary also you can calculate the normalized value. And here you see, like, now after normalization, both age and salary column will have value in between 0 to 1. So that dominating factor will not come in place. So that's where, like, this helps you basically. Okay. Now let's understand what is standardization. So standardization is also known as Z-score normalization. So because it is something related with Z-score, you will see in a moment. In standardization, features are scaled to have zero mean and one standard deviation. So after once you standardize the value of particular feature, then you will see, okay, standardized values have zero mean, and if you calculate the standard deviation, you will find it is equal to one. So that is the main properties of standardized features. Yeah. So what is the formula used for? So x standardized value is equal to x minus mean divided by standard deviation of x. So to calculate the standardized value, you need to have the mean value and the standard deviation. So here we are dividing by standard deviation, right? So that's where I said, okay, it is related with, it is also called a Z-score normalization, correct? So it will tell you, like, how many standard deviation away your values are from the mean point. Okay, that's the definition of Z-score. So let's see how we calculate the standardized value basically. So here, if we talk about the age column, okay, so to get the standardized value, we need something called mean. So you just first calculate what is the mean for these value. Okay, mean is nothing but you just sum those value and divide by all. I mean, divide by the number of how many values are there. 1, 2, 3, 4, 5, 6, 7. There are 7 values. Okay, just sum all these values and divide by 7. You will get the mean value. Okay, and then you need something like standard deviation, right? So what is standard deviation? This is nothing but the square root of variance, right? And variance is like x minus x bar whole square divided by n, right? This is your variance. So for each data item you need to calculate. Okay, so if you put the like 44, 27, 30 all here. Okay, this is xi. So like 44 minus mean whole square plus 27 minus mean whole square plus 30 minus mean whole square up to 48 minus mean whole square divided by n. N is 7. Okay. And then take a square root. That's how you get the standard deviation. And then for each value in age, you put those mean and standard deviation here, and you will get the standardized value. Right. So this is what you will get. And if you calculate the standard deviation for this, you will get the standard deviation will be equal to 1. And similarly here for salary column also, standard deviation will be 1. For this, standard deviation will be 1. And this will have mean value is equal to 0. Okay, so this is what standardization means basically. So let's understand some more important points like where to go for normalization and where to go for standardization. So if you have outliers in your feature, in your column, then normalize, what normalizing will do? Normalizing your data will scale most of the data to a small interval, that is a 0 to 1, right? Which means all features will have the same scale, and hence it will not handle the outliers well. It will just ignore the outlier effect, right? So that's not something desired. So that's where standardization is more robust to outliers, and in many cases, it is preferable to go for standardization rather than opting for max min or min max normalization. Okay, so standardization is more preferred choice compared to min max normalization. Normalization is good to use when you know that distribution of your data does not follow a Gaussian distribution or normal distribution. So this can be useful in algorithms that do not assume any distribution of the data, like k nearest neighbors and neural networks. Okay, so like k nearest neighbors or neural networks algorithm don't have the assumption like your data set should be normally distributed. So those kind of algorithm you can go for normalization. Okay. Another point is like standardization, on the other hand, can be helpful in cases where the data follows a Gaussian distribution. However, this does not have to be necessarily true. Okay, this is important. And unlike normalization, standardization does not have a bounding range. So even if you have outliers in your data, they will not be affected by standardization. So that's where I told standardization is more preferred choice because it is robust to outliers, but normalization is not. Okay, so this point you keep in mind. So that's all about normalization versus standardization. Let's discuss another question, that is what is bias variance trade-off. So to understand bias variance trade-off, you should know like what is bias error, what is variance error. So let's understand what is bias error. So bias are the simplifying assumptions made by a model to make the target function easier to learn. So what is bias basically? So yeah, when you use a very simple model, okay, very simple model, then what happens? Your model becomes biased towards a particular data set, okay. So that's where it doesn't give you proper accurate result in prediction. So that's where we say, okay, model is high biased and it is not correctly identifying the, it is not correctly predicting whatever we want to predict. So generally, linear algorithms have a high bias, making them fast to learn and easier to understand, but generally less flexible. In turn, they have lower predictive performance on complex problems that fail to meet the simplifying assumptions of the algorithm bias. Okay, so the algorithm like linear algorithms, which are very simple, okay, they do fast learning and they are easier to understand, but generally less flexible, right? So that's where they don't produce that much accurate result in some of the cases. So what is low bias basically? Low bias suggests less assumptions about the form of target function. So low, in case of low bias, model take less assumptions about the target function. It doesn't make many assumptions, okay? And in case of high bias, it's opposite. In case of high bias, it model suggests more assumptions about the form of target function. Okay. So example of low bias machine learning algorithms include decision trees, nearest neighbors, and support vector machine. So they have low bias basically, and logically our model should be low in bias, right? It should not be biased basically. Otherwise, it will produce wrong result. An example of high bias machine learning algorithm include linear regression, linear discriminant analysis, logistic regression. So you keep these algorithm in mind. Sometimes interviewer asks, okay, give me some example of high bias algorithm, give me some example of low bias algorithm. Okay, so that's where you should keep these in mind. Like these are the low biased algorithms, and these are the high biased algorithm. Like simple algorithms are high biased normally. Okay. So now next is like what is variance error basically? Variance error is the amount of change in the estimates of the target with the change in training data. So what it tells basically, suppose you have trained a model, you're ready with the model, and now you're doing some change in your training data. Maybe you are getting some another sample. Then how your trained model is behaving, okay? How much whether it is I mean it has learned properly the new features or new behavior coming in that next sample, and it is able to predict the result correctly without training it further, right? So that's where, and if it is not the case, then variance error occurs. So variance error is the amount of change in the estimates of target with change in training data basically. Logically, model will have some variance. However, it should not change too much from one training data set to another training data. Okay. So what it is telling logically, when you change the sample, so model trained model will have some sort of variance, right? But of course, that variance would not be very high, right? So that's where we no need to. I mean, it should not be needed to retrain the model on every sample basically. So it should easily absorb the sample change basically. So that's what it is telling. In simpler terms, it means model should be good at picking out the hidden underlying mapping between the input and output variable. Okay. So ML algorithms which have high variance, those are influenced by the specifics of the training data. Keep this in mind. So now there are certain low variance algorithm, there are certain high variance algorithm. So low variance algorithm are suggests small changes to the estimate or the target function with changes to the training data set. Okay, if you change the training data set, so in estimates of the target function, there will be only a small change. Okay, your estimate will not vary much with respect to your training data. Then you say, okay, it is low variance. And what are the algorithm of low variance? Like linear algorithm, linear regression, linear discriminant analysis, and logistic regression. Okay, keep this in mind. What is the high variance? So high variance suggests large changes to the estimate of the target function with changes to the training dataset. If you change your training dataset or if you get a new sample, then there will be large amount of change in the estimate of target function. Okay, so that's where like a decision tree, k nearest neighbors, and support vector machine comes in place. Okay, so these are high variance algorithm. So generally, non-linear machine learning algorithms that have a lot of flexibility have a high variance. For example, decision trees have a high variance that is even higher if the trees are not pruned before use. Okay. Now you understood what is bias error, what is variance error. Now let's talk about what is bias variance trade-off. So as we understood in previous slides, to have good predictive power or good estimates on target feature, algorithms should have low bias and low variance. There should be a balance between them. High bias, it's also an error. High variance should also not be there. So there should be a trade-off. Okay. So linear. So linear machine learning algorithms often have a high bias but a low variance. Correct. So they are highly biased because they are simple algorithms. So they don't understand too complex data. So they start behaving like a high bias. And non-linear machine learning algorithms often have a low bias but a high variance. Okay. So now the parameter. So how we deal with that one? So we set some kind of parameters within our algorithm. Okay. So the parameterization of machine learning algorithm is often a battle to balance out bias and variance. If you increase the bias, it will start decreasing the variance, and if you decrease the variance of the model, it will start increasing the bias. Okay. So there should be a balance between both of them. Okay. So generally, low bias and low variance algorithm is preferred. So let's understand with a graph. Like see here, in x-axis we have a model complexity, and y-axis we have a error. Okay. So now if you start increasing the model complexity in x-axis, okay, like this in this direction. So what will happen? Like you start making your model more complex and more complex, then of course it will have less bias. Okay, but simultaneously, what happen after a certain point, its variance will start increasing. So you don't want model to be of high variance, right? Because if there is a high variance in your model, then the moment you change your training data, it will behave differently. Okay, then you need to again retrain it. So that's where your model complexity should be balanced. It should not be very too complex model. And similarly, if it is a high, I mean, you are increasing the model complexity, of course, bias error will be less, but variance error will be increasing. So that's where total error is also increasing. But other hand, if you have too less complex data, your model is very less complex, so it will not have all the behavior included within it. Okay, so that's where it will be having a high bias, and of course variance will be very less, but it will be having high bias. Again, if it is a high bias, then there are I mean more errors in that one. Okay, so that's where we say, okay, there should be balance in between. So you have a balanced complexity within the model, and that's how you will project the low bias and low variance in your data point. So this is the point of low bias and low variance. Okay. So this is another good example. I mean, plot of bias variance trade-off. Here you see like if you have the middle circle is representing the predictive power, predictive nature, and then yeah, this one middle circle, right, in each one. So this middle red one basically representing the predictive model. So if you have a low bias and low variance, so you see like you have very high predictive power, and the moment like you increasing the bias, okay, your data points are going away from the middle point, right, and still they are scattered in one place because they have less variance. Okay, but if you have low bias and high variance, then the data point will be scattered all around the circle basically. And if you have high bias and high variance, then both they will be they will be going away from the middle point, and they will be scattered also, right? So that's where low bias and low variance is preferable. So this one is preferable. So now next question comes like, what is overfitting and why it occurs? Let's understand. So in one-liners, when the trained model is not able to generalize the learned behavior on the unseen data, then we say, okay, we have encountered the overfitting problem. So basically, when we do training, right? So a model start understanding the behavior, the pattern about your data. Okay, but when you start predicting something on test data, then if same behavior, whatever it has learned, a model is not able to generalize on test data, then you say, okay, overfitting occurs because it is working perfectly fine in your training data, but it is not working fine on your test data. So that's where you say, okay, overfitting occurs. So what does it mean when we say generalize the learned behavior? In machine learning, when the model performs well on training data but not giving the near to same level of accuracy on test data, then we say that it is the indication of an overfitted model. That's what I told, right? It has learned the behavior on training data, but it is not able to generalize the same behavior on test data. So that's where it will not have the same level of accuracy in test data. So that's where if you observe this kind of behavior, then you say, okay, okay, model is overfitting. So one more case could be like your model is performing well on both training as well as testing data, but not performing well after the deployment on live data. So this is a case of like advanced form of overfitting. The reason for this advanced level of overfitting is that when we split the original data into train and test, they both have similar characteristics and hence it performed almost similar in training and test data, but after deployment the real data differs in terms of the characteristic and hence due to overfitting the model could not perform well. Okay, so this is also a case basically. So this is when you understand, okay, your model is overfitting basically. So this, beautiful picture I got from Geeks for Geek. So just for understanding purpose, so you see like there are three pattern here. First one is underfitting, second one is appropriate fitting, and third one is like overfitting. So in underfitting, you see here, so it is not able to classify the cross and bubbles properly, right? So it is very underfitted, like predictive power is very less. And in third one, like it is almost accurately correct classifying each and every point, right? So that's where why we say it is overfitting. Okay, because like in training data it is clearly identifying each and every point, but there could be case like when you give the unseen data or test data, right? So that's where it will start it decreases in terms of error, like predictive power, like it may not able to identify all the data points. So that's where we say, okay, this is overfitting problem. Logically, this middle one, right, appropriate fitting, this is the desired behavior basically, right? So here you see like it is able to classify all the bubbles perfectly, but it is misclassifying those two crosses. So this is the ideal behavior. So now next thing is like we should understand like what are the reasons behind overfitting. So when a statistical model describes random error or noise instead of underlying relationship, then overfitting occurs. So what is this? So when you have lot of noise in your data set or lot of features which are not adding any value in your data set, okay, then what model start doing? Model start understanding that noise, those, unvalued features, okay, then it start learning those behavior instead of the actual pattern, actual behavior, right? So that's where overfitting occurs basically. When a model is excessively complex, overfitting is normally observed because of having too many parameters with respect to the number of training data types. Also, in simple terms, we say like when model starts learning the noise instead of learning the actual characteristics, then overfitting occurs. So you just remember this third point. This is in very simple term. When model starts learning the noise instead of the actual characteristics, then we say, okay, now overfitting occurs. Okay. The possibility of overfitting exists as the criteria used for training the model is not the same as the criteria used to judge the efficacy of a model. Right? So this could also be one of the reasons why overfitting occurs because you have not used the same criteria on which you have trained the model, but you are using this different criteria for testing the model. So that could also be a reason for overfitting. So you have to check these different reasons. Okay. So now next question is like different ways to avoid or overcome overfitting. What are the different ways? Okay, so let's understand. So the first very important method is like cross validation. So what you do in this cross validation method basically? So in cross validation, you divide your data set in k different samples, and you start training your model on k minus one sample, and you keep kth sample for testing. Likewise, you iterate this k times. What you do basically, in each time you keep different kth sample for testing, and remaining k minus one you use for testing, training the model. Okay, so in each kth iteration your model is trained on k minus one sample and will be tested against kth sample, and then you take the average of performance, like average of accuracy. So that's how you do cross validation works basically. So this is one of the important technique used for overfitting. Another technique is like feature selection. So apply the feature selection techniques like PCA so that it removes the irrelevant features and hence reduces the noise. One of the cause for overfitting. Okay. Another is like early stopping. So while tuning your model, do testing against the test data and see if it generalizes well. Stop at the point where it starts increasing the error on the test data, right? So like you see in that like model complexity versus error graph, right? If you start increasing the complexity, then after a certain point, like model variance start increasing and bias is anyway low. So then if variance is increasing, then error is also increasing. But if you have too less complex data, then of course the bias will be high. So that's where you have to have a trade-off. So that's where if you you do the training and you keep on doing, and you stop the point where it again start increasing the error. So that's where we say okay, early stopping. While tuning your model, do testing against the test data and see if it generalizes well. Stop at the point where it start increasing the error on the test data. Another method is like regularization. So regularization works by assigning different weights to the features based on their importance and impact on the problem we are solving. It also adds the penalty term to the cost function to manage the data bias. Okay. So next is like ensemble techniques. Under ensemble techniques, like we have bagging and boosting. So yeah, so these are the basic, important methods for avoiding overfitting. So here in this session, I have just named. I have not gone in deeper. So like because each method will take some 10 to 15 minutes to describe. Okay. So so in next session, I will be talking in detail of each of these methods. So stay tuned. So I think so that's all for today's session. And yeah, so if you have not subscribed my channel, please subscribe and click the bell icon so that you'll get notified each time when I publish a new video. So thank you.